So all of our units here on macromolecules have sort of been set up the same. We learn about structure first, then we learn about function, and then we sort of have some applications. So same is going to be true here. What's unique about lipids compared to any of the other macromolecules that we've really learned about is we really need to think about their hydrophobicity. Now, we did learn about the hydrophobic effect at the beginning of the semester. We talked about the hydrophobic effect being sort of the driving force for protein structure when we have those nonpolar amino acid side chains that want to be in the center of a protein. But let's remember what the hydrophobic effect is. It's the tendency of nonpolar substances to minimize their contact with water. So when we have something like fatty acids or triglycerides, or we'll talk about phospholipids, what we really have is something that's what we call amphipathic. It actually has both sort of characteristics. It has a hydrophobic nonpolar part and then a hydrophilic part. So we need to think about, when we talk about structure, sort of how these will sort of assemble to form sort of macromolecular structures. So we just finished in our last video talking about how we can take triglycerides, we can hydrolyze them, and we can generate free fatty acids. And so these free fatty acids are what we can use to make soap. So detergent molecules are going to sort of resemble synthetic fatty acids, but told a story about, the origin of soap. Soap is actually made and used to be made from fat. So what happened on the top of Mount Sapo, right, is they would sacrifice animals. So you sacrifice an animal, you put it on a spit, and then the fat drips down into the wood ash of the fire. Wood ash is very, very basic. So what we're fundamentally talking about is the base promoted hydrolysis of triglycerides and fat to generate free fatty acids. So what we have here is we have free fatty acids, and if we think about what a fatty acid really has, it has a large hydrophobic tail and then a hydrophilic head group in that carboxylic acid functional group, right? So I want you to think about structurally these sort of resembling like the drumstick ice cream cones, right? We've got the cone part, and then we've got essentially like a golf ball on the head. If we wanted to have all of these assemble according to the hydrophobic effect, the tendency of nonpolar substances to minimize their contact with water, what that means is the cone part really wants to all associate with other cone parts. And then we've got the ice cream part, that's the hydrophilic head, wants to be on the outside. So what this ultimately means is that we're going to have assembly of these fatty acids into something that we call a micelle. That's a spherical particle, okay, where the interior is the greasy hydrophobic core that is all of those fatty acid tails, and then the surface is all hydrophilic because it is those carboxylic acid functional groups, okay? So how does this mean that soap can clean? Getting back to sort of our story here, we would have those animals that would be sacrificed on the top of the mountain. They would be burned on a spit. We would have the fat drip down into the wood ash, into the lye. Now, what happens is it rains, and that mixture flows down the mountainside, and it flows down to the river that's down there. Well, lo and behold, people thought the gods had given them magical cleaning agents because whatever came down from the mountain, from Mount Sapo, they called soap, and they used it to clean their materials. So soap is actually made from fat so that it can clean fat. And here's how it works, right? We've got these micelles that we have here. These micelles have a hydrophobic interior and a hydrophilic surface. So they're like these little beads that are able to be dissolved in water because they're hydrophilic all on the outside. But what's going to happen is they're going to take dirt and grease, and that dirt and grease being hydrophobic, which is why you can't rinse it off of your clothes, it's going to want to interact with the inside of that micelle. And so it gets trapped inside. And then because the entire water or micelle is water soluble, you're going to be able to rinse it down the drain. So I think it's not coincidental that a scrubbing bubble kind of looks like a little micelle, right? So that is how soap is made and how soap cleans. All right, so that's free fatty acids. When we talk about phospholipids, that's taking two fatty acids, hooking them onto a glycerol backbone, and sort of having this third area be free. And when we talk about membrane transport, and we'll talk about lipid bilayers and so forth, we'll talk about what you actually can put on this third position. But the idea is you only have 2 fatty acids. Now, when we think about the structure that we have here then for this is a phospholipid. Phospholipids are not going to be sort of ice cream cone shaped. They are really going to be cylinder shaped. And when we think about the hydrophobic effect coming into play and having macromolecular structures of phospholipids, we're not going to have them form spheres because their molecular shape really doesn't afford that. What's going to happen is they're going to associate into bilayer sheets. Okay, and even though this shows this kind of wrapping around here, the reality is we form these giant lipid bilayers. Okay, so we've got lipid bilayer, or LBL. And this is what we see on all of our cell surfaces. Okay, we've got this lipid bilayer, which has a top and a bottom, an outside and an inside layer that's very happy to be in an aqueous environment because it's very hydrophilic. And then the interior of it is very nonpolar. Why this is important is it allows us to impart compartmentalization and prevent transport of substances that we don't want to be able to freely transit across a lipid bilayer. In our next learning unit, we will talk about membrane transport, and we will talk about things that can freely diffuse back and forth across a lipid bilayer. Those are going to tend to be nonpolar substances because they can freely diffuse within that nonpolar core of a lipid bilayer. Okay, when we have other substances, we are going to need to find mechanisms to traffic them across lipid bilayers. What this is generally going to mean is we are going to have proteins that are embedded in a lipid bilayer that serve as gates that are going to allow us to move things back and forth. So this is where we're going to have membrane transport come into play. And you may have heard about something called the fluid mosaic model when we sort of describe lipid bilayers. Well, the fluid model really corresponds to sort of this lipid sea that we have. And then we talk about icebergs sort of floating in this lipid sea. The icebergs are really the proteins that are going to be responsible for transiting molecules across our lipid bilayers. So an entire learning unit on that, and then we'll have a case study to understand how cholera toxin sort of affects some of these membrane transporters. All right, the last piece, and this is going to lead into our next topic, which is on cholesterol and lipid trafficking in general, has to do with what we think about with triglycerides. So triglycerides generally are what we find in our dietary fats, and it's what we find in our storage fats in our own bodies. Okay, the key here is when we think about this macromolecule, when we think about this fuel molecule, we are talking about something that is hydrophobic. And unlike any of our other macromolecules that we've talked about, that means we're going to have transport issues. When we talked about carbohydrates and specifically glucose as a monomer, we didn't need to worry about that being transferred throughout your bloodstream because it's very hydrophilic. When we talk about many amino acids are hydrophilic. They're going to be able to circulate without issue. When we talk about lipids, and lipids is really a catch-all for anything that's nonpolar, we are going to talk about, we've a lot of time here talk about triglycerides, but we are also going to talk about cholesterol, and we're going to talk about specifically vitamin D. And a lot of these sort of all come into play when we talk about overall cardiovascular health. So we'll sort of tie all these pieces together at the end. But when we think about transit issues, how we sort of facilitate that is we talk about trafficking lipids in particles. So we have lipoproteins that we are going to have. So we're going to have, this is what we have up here, a lipoprotein, okay, which is a combination of lipid and protein. And this is really a vehicle for transport. And specifically, when we talk about what's being transported is the lipid piece. And this protein piece, again, is going to be what is hydrophilic, but so it's going to increase solubility, but it also has some important implications for how we traffic things. Okay, so this protein piece serves 2 general roles, is it increases the solubility, And here's that protein piece here. It's that purple that we see there. It's a protein that literally wraps around this lipid particle. And so this is actually more like a large micelle that's shown here, but we also can have sort of a lipid bilayer that we have there. But the protein that wraps around is going to increase solubility, but importantly too, it's going to impart directions. Well, what do I mean here? Well, the amino acids and the things that are present on this protein are going to be like the bus ticket directions. We're going to talk about a lot of these like trafficking, like a bus. And we're going to talk about whatever is displayed as the sort of ticketing information on the front of that bus is going to direct where it goes. And that ticketing information is this protein. Okay, so taking a little bit of a closer look at this very simple representation of a lipoprotein. So again, lots of lipid that we have here. The purple represents protein, but we can see here we've got phospholipids that we have here. Cholesterol is a really important, not only passenger potentially, but also a plasticizer. So cholesterol that we have here, I'm going to highlight that it can be referred to as a plasticizer. And what that means is it's going to modulate membrane fluidity. So remember, there's lots of molecules that we're going to learn about here that get a bad rap, like saturated fat and cholesterol, but are really important molecules in your body. You synthesize them yourself. Anything that you synthesize yourself, I don't want you to think about as being bad. What makes many things problematic and bad are the context that we find them in or the environment that we find them in, particularly if we find them in a pro-inflammatory environment. Okay, so we've actually already learned about some lipoproteins, right? We learned about apolipoprotein E, ApoE. That's important for trafficking lipids, okay? ApoE comes in those ApoE3 and ApoE4 isoforms, and we talked about the implications of those with Alzheimer's disease. They actually have implications with cholesterol trafficking and so forth, so we're going to learn a little bit more about those ApoE proteins. But when we pick up and we move on and we talk about cholesterol, what we will talk about is cholesterol is neither good nor bad. Cholesterol is an organic molecule. What gives cholesterol its context of being good or bad is what it is trafficked with. Is it trafficked as part of an HDL particle? HDL particles have a different purple protein that we see on the outside. That is going to direct it in a different way than we traffic LDL particles. Okay, so a lot of lipoprotein trafficking that we'll talk about in our next video on cholesterol.